So in section 3.2, we looked at addition and subtraction for the whole numbers. And then in section 3.3, we're going to look at multiplication and division. And we're going to do kind of the same thing with 3.4 and 3.5. 3.4, we're going to look at algorithms. We'll talk about what that is for addition and subtraction. And then 3.5 and 3.6, we're going to use algorithms for multiplication and division. So today we're going to do a lot of what we did last time, but in regard to multiplication. So to start with, multiplication of whole numbers. For finite sets A and B, if the number of elements in set A is little a, and the number of elements in set B is little b, n does not equal 0, then n times A would be A added together how many times? N times. Okay, so this idea that multiplication is simply repeated addition. And if we do have n equal to 0, then 0 times A by definition is 0. We're defining it that way. And if we have A times B, then this is the number of items in the cross product of A and B. Cartesian product, sorry. We used Cartesian product before. In other words, n of A times n of B would be n of A cross B. All right, when we did addition, we had 2 models for addition. And then we did subtraction, and I think we had 4 models for subtraction. Maybe we even had 3 models for addition, I can't remember now. We're about to do multiplication, and we're going to have different models for multiplication. I think there are 3. Yep, there are 3 models for multiplication. All right, you guys ready to look at the 3 models for multiplication? All right, just with addition and subtraction, the difference is sometimes in the way that we visually sort of draw them, and sometimes the difference is in the way the word problems are created, which is what we did with subtraction. So here's an example model for multiplication. Giselle takes 3 tests every Friday. After 4 Fridays, how many tests has she taken? And we understand that that's 3 times 4, right? But this is an example of repeated addition. Really and truly, this looks like 3 this Friday, 3 next Friday, 3 the next Friday. Very, very visually, this is the same as 3 plus 3 plus 3 plus 3. And of course, if we were to count them, this is 4 times. Right? This is 4 times 3. And of course, the answer is 12 tests. But the very way that it's even described sounds like it's addition. And if we did this too many times, we wouldn't want to add them physically together, right? I mean, that process would become cumbersome, truly. And so, 4 and 3 of them is not too many, but if we had 15 of them, that would start to become annoying, is what it would really be, right? It would be annoying. So this is a repeated addition sort of a perspective for multiplication. An array, okay? So an array model, Minhu is baking cookies. He is able to place the cookie 3 cookies wide, the cookie dough, sorry, 3 cookies wide and 6 cookies long in his pan. How many cookies will his pan hold? And as soon as I described cookies on a pan, you all visually created in your mind an array model. You did. Visually, you have seen this happen enough times that you know what it looks like on a cookie sheet. So we're going to draw this cookie sheet. This is a really good example, right? Like, could we draw the 3 tests and the 4 Friday? I mean, like, we could, but it just doesn't beg us to do that, right? This begs us to draw a picture. It feels like a different kind of description. So we had 3 cookies wide, 6 cookies long. So I feel like my cookies should at least be brown. They definitely should be brown, right? Here are my cookies. They look like donuts. I should change the problem. Donuts in that's what I really should do. I should do donuts that you get from the bakery next time. All right, so we have these 6 wide or 6 long. All right, so we have our holy cookies. There are 3 in one direction, right? And there are 6 in the other direction. Of course, we can count, we can multiply. It's the same idea. But there are a total of how many cookies? Yep, 3 times 6 are 18 cookies. And I mentioned this last time, I'll mention it again. If we're dealing with a physical example where there are units, in as much as cookies is a unit, we're going to write down what it is. This is 18 cookies. The last one was 12 tests. Okay, so the picture is what we visibly see in our head, or sort of mentally see in our head when we create this word problem. The third model is an array model. Is an area model. The second one was an array model, an area model. So this is going to feel very much like the array model. It's just that it's used for measurement of something instead of counting objects, physical objects. Alexis is planting a garden. She has a space that is 5 feet wide and 7 feet long. How much area does she have in which to plant? So what am I visibly going to draw? A rectangle. And in my rectangle, it is 5 feet wide. I'll draw mine on the inside because I have more space. 5 feet wide. And how many feet long is it? 7 feet long. I totally put up those in the wrong direction. Let's put the 5 over here then. 5 feet wide and 7 feet long. Of course, not drawn to scale. Now, this is fine, and we can actually do the multiplication here. It's perfectly fine to talk about it like this. If we were wanting to justify to a child why this is actually 7 by 5, or 7 times 5 to give me the 35, what could I do in my picture to further justify what I'm trying to argue here? What could I do? You're really close to what I want to do, but it isn't the sides. What is area? Okay, so you're thinking volume. That's volume, length times width times height. Somebody said length times width for area, which is correct. Okay, but that's why I did the 7 by 5. But why does that work? It's something about the space inside, right? Okay, so what if I did something like this? I'm going to have to change my picture because I got too much going on now. But what if I did this? We'll use these. Okay, are there 5 of these now? I think there are if I count them. 1, 2, 3, 4, 5 rows, if you will. And I could make, again, this is not an accurate drawing at all. There are 7 columns now if I've done that part at least right. Oh, that's good. They're not perfectly square because my picture is lopsided, but could I actually count the individual little boxes? I could, and especially if a child wanted to justify why length times width actually is area, or why the area model ends up being multiplication or something like that. This is a really good picture justification for that. It's a grid, right? And could you even use graphing paper, the grid graphing paper? You could. So you could justify this by actually having graphing paper to make it the 7 feet long and the 5 feet wide kind of thing. Okay? So there's our model for multiplication, our third one. Now this is different. It really is different than the array model in the sense that we're talking about a length that we're measuring in each case. Each measurement was feet, right? Whereas over here, the cookies were physical objects. I was counting the objects. Over here, I'm counting the spaces, right? The objects' spaces instead of the objects themselves. So there is a variation to this. So what I'd like for you to do next is in your groups, you're going to create 3 word problems. You don't have to draw the pictures, okay? You're creating the word problems that describe these 3 different types of uniquely different models for multiplication. So in your group, create 3 word problems, and we'll take about 5 minutes to do that, and then we'll come back together and share those. All right, who would like to give us their example for repeated addition? Don't everybody jump up and down at once. Emily, do you mind?
No.
Okay.
Sam has 6 baseball games every Thursday night. How many will he have after school?
Ooh, he's going to be busy. 6 baseball games every Thursday night. Maybe he's reffing. Is that what it is? He's the ref. Okay. So, and it's Little League, and so they're only going to be like, 25-minute games. That'll be good. All right, so we have so many games every so many nights, and we have the total amount at the end. Very good. All right, how about an example of an array model? Caitlin.
Betty is baking biscuits. She places the dough 5 biscuits long, or 5 biscuits wide and 7 biscuits long. How many biscuits does she make?
Fantastic. Biscuits do usually bake in an array. That makes sense, right? Yeah. What other example did we have for an array? Let me do one more array, and then we'll do one area model. So which of the two groups wants to do their array model?
We put Lacey is baking cupcakes. The pan has 4 cupcakes wide and 5 cupcakes long. How many cupcakes is she making?
Awesome. Cupcakes definitely bake in a pan that is an array model, don't they? They do. Good job. All right, and then the last one is an area model. What else do we have for area? What do you guys have?
Joe's making a mud pit. It's 27 feet long and 18 feet wide. What's the area of Joe's mud pit?
Fantastic. And that mud pit would appeal to the boys in the room especially, right? Because mud pits are exciting.
They really are fun.
They are fun, I know. There's one at the campground that my kids go to every summer, the mud pit. Some other things that are arrays. So you guys, we did baking examples, and those are fine examples, but what are some other things that you guys can think of that could be done in an array?
Classroom.
A classroom, the desks in a classroom, that's a good example. What else?
We did hay bales on a trailer.
Fantastic. Hay bales on a trailer, that's great.
Cars in a parking lot.
Cars in a parking lot, okay, that's good. What about 12 packs of soda or 24 packs of soda? Those are pretty good examples. What else?
Stands in the bleachers.
Stands in the bleachers, okay. Toilet paper's another one, or paper towels. Those are often packaged that way. So those are some other ones that I'll sometimes see examples with. All right, so great examples. Good job, guys. All right, let's take a look then at some properties for whole number multiplication. You'll see some of the same properties we saw before, and there's at least a couple additional properties as well. Closure property. We had that work for addition and not work for subtraction, right? Closure property. So the closure property says, in this case with multiplication, that if you multiply 2 whole numbers together, you get another whole number. Now, we talked about last time about the fact that closure matters for the operation. It also matters that you're looking at specific types of numbers, right? So this works for whole numbers. Would this work for, we did an example where it worked for whole numbers with addition, but it didn't work for whole numbers with, not whole numbers, for odd numbers with addition, right? Odd plus odd does not equal odd. Let's do the same thing for odd numbers with multiplication. Does an odd times an odd equal an odd? Just sometimes?
I'll try to.
Anybody bold enough to say all the time?
Sure, it's all the time.
It is all the time, actually. Yeah, because the only way that you get an even number is if you have a 2 as a factor, and the 2 will never be a factor of an odd number. So an odd number times an odd number is always going to be an odd number. So odd numbers would actually hold for this one, but it didn't hold for addition, right? So that's a unique feature. It matters what number group you're working with, as well as the operation. So multiplication with whole numbers works. Commutative. What happens when you multiply 2 numbers together? Does it matter the order you multiply? Not at all. A times B is B times A. Commutative property holds for multiplication. The associative property, there's one of those for multiplication as well. A times B times C. Remember, they go in order A, B, C, A, B, C. It's the groupings that are different. So on the left, you've got the A and the B grouped together. And on the right, it's the B and the C grouped together. And we end up with the same value no matter the grouping. Now, we had an identity property for addition. What was the identity element that we used? What number was it?
0.
It was 0. So it's really important for us to realize that when we're talking about identities, we need to say that it's the additive identity or the multiplicative identity, because they're different, right? The additive identity is 0. What's the multiplicative identity? It's 1. Okay, so make sure that when you're specifying what property of something you're working with, that if it's an identity property, you say additive identity or multiplicative identity, because they are different. The multiplicative identity is the number 1 because A times 1 and 1 times A both equal A. Okay, so the identity element is 1. The identity property is that A times 1 equals 1 times A is equal to A. Okay, so those are the same. We had those same 4 properties last time where we had, closure, commutative, associative, and identity. The new properties that we have this time are the 0 property. 0 is wonderful. Multiplying by 0 is like super fun, right? Because you're going to get it right. 0 multiplied by something is just zeros everything out. A times 0 is equal to 0, and 0 times A is equal to 0. Wonderful property. And then we have a property that combines multiplication with the addition or subtraction that we had in the last section. So when we have the distributive property A times B plus C or B minus C is the same as AB and then plus or minus AC. It distributes over addition and subtraction. So the last thing we're going to do is you're going to flip your page over once you get this one written down. And you have, I think there's 6 of them. Looks like 6. And we're going to do like we did in the last section. You're going to identify which property is being used in each example. And it is just one property per example, okay? So I'm not throwing like 3 properties in there and telling you, like, oh my goodness, you're right, but you're sort of not right. No, there's one per example, okay, or there's one property per example, but that doesn't mean that the properties might not repeat. So like there could be 2 commutative properties on here or something, and there could be like no identity on here or something like that, okay? So it's not, 6 properties, 6 examples. So go ahead and figure out which of the 6 properties are being used in which of the 6 examples. Once you have something written down for all 6, and if you can't figure one of them out, it's okay. Call it good for now. Compare with your group and see if you can come to a consensus on which of the 6 you think it is for which of the 6 examples. As you're comparing, see if you can come to a decision together. If you can't, it's okay. We'll come to a decision as a group together, but try to do it within your group if you can. Abby's still working. Is Abby behind? You guys are already done, aren't you? I saw you do that. That's right. Okay, good deal. Okay, what did you guys get for A? That is the 0 property. Good. How about for B? Good, that's commutative. That's another one where there's 3 in there, so it's sort of meant to make you really think, but it is commutative because what's really changing place is the 3 and the 4, right? The parentheses don't switch anything, just the 3 and the 4 switch. What happens on C then?
Associative.
That's associative. Don't abbreviate that one. That doesn't work very well. So we group the 7 and the 3 differently in each case, right? Yeah. How about D?
Identity.
That's the identity. Good job. Now we need to be careful. Which identity is it? There we go. We'll put multiplicative. You can abbreviate multiplicative, but make sure it's in there. Identity. If you only write identity down on a test on this example, I will make you redo it because I want to make sure that you can identify which of the 2 identities it really is. What about E? That's distributive. Good job. And F. That's also distributive. It's kind of a funny looking one, but it is distributive. On that one, what you have to recognize is that it is the whole 1 plus 2 that is distributed to the 3, and then the 1 plus 2 that is distributed to the 4. Good job.